I'm Mr. McBrien. This is SCH4U, Polymers. The Ontario curriculum would like for us to be able to, in addition to discussing general organic reactions, be able to talk about polymerization reactions, specifically addition and condensation polymerization. So what we'd like to do is get a feeling for the underlying structure of some polymers, talk about how they're put together and some of the importance of them, and then contrast an addition reaction with a condensation reaction. On your own, we'll give you the opportunity to research the production of several polymers as part of the worksheet for today. Polymer chemistry is significant not just from an industrial point of view, but also from a biological point of view. This is because macromolecules, polymers, can be both natural and synthetic. So here we see three different materials that are made of polymers of various types. Now, really, in many ways, polymer chemistry is no different than standard organic chemistry. We just do it on a larger scale. So the same reactions that we use to make small molecules are the ones that we use to make large molecules as well. So if we react two molecules of ethylene together, we get this 1 butene molecule. However, if we keep adding more and more ethylene molecules, keep stitching them onto the end of the molecule that results, eventually we wind up with polyethylene. Now, one thing that we need to keep in mind, so here's polyethylene here, and again our N value can be hundreds or thousands, can be the value for N. When this occurs, the end unit chemistry becomes less and less important, because if we imagine 1,000, if N equals 1,000 here, then it's 0.1% is associated with the end of this macromolecule. And it's far more important what's going on in the center of the molecule than on the edges. And it's for this reason that we can produce such interesting materials from those simple monomer feedstocks. So that addition reaction to create polyethylene is one possibility, but we can react amides to produce polyamides in a similar fashion, except in this case, notice that our reaction is a condensation reaction. So one of the products is our macromolecule, and the other is a molecule of water. These long-chain polypeptides are also called proteins, of course. Now we can use a similar reaction, a similar condensation reaction in factories and produce from carefully selected molecules produce nylon 66. The 66, of course, just referring to the number of carbons associated with each of the blocks in the copolymer. There are lots of other polymers that we can produce, some from different monomers, some from different reactions. So if we react ethylene in an addition reaction, we get polyethylene, and we can have films or coatings for milk cartons and toys and things. If we add a chlorine and then produce that same addition reaction, we wind up with polyvinyl chloride, or PVC, and it has slightly different properties, and so is used for typically things that need a little more flexibility than polyethylene. Styrene, again, an addition reaction, but it has a benzene ring off the side. Everybody's familiar with polystyrene and its use in packing materials. And similarly, we can have methyl methacrylate or tetrafluoroethylene. These addition reactions all produce polymers with slightly different properties. Teflon at the bottom is particularly interesting because it's such an inert material. It's chemically resistant. It, of course, is non-stick in fry pans. Now, polymers in theory are extremely inert and safe to be in contact with food. However, some impurities that we'll see in polymers can be a concern. So in particular, we can look at bisphenol A, and it is kind of a nasty customer. It mimics estrogen, and there have been statistical links between it and cancer, diabetes, obesity. Really, we want to avoid having that in contact with our food for sure. Now, polymer chemistry is in some ways a very mature science. However, there have been some very interesting innovations in recent years. And in fact, there is a lot of interest being paid to the ideas of nanocomposites and nanomaterials in general. So a couple of quick notes about that. Nanocomposites, nanomaterials, are the combination of multiple materials to form something new with the ideal properties of both, and sometimes the synergy gives it unique properties that can't be achieved in any other way. Nanotubes are a particularly interesting composite. They're based on the chemistry of fullerenes, and what can be done is to stretch this soccer ball shape into an extremely long single-walled carbon nanotube. And this is essentially one molecule, such that it's about 1/100,000th the thickness of a strand of hair. Now, that in itself is interesting, but if we create a material from carbon nanotubes, it's interesting to note that the strength is more than 100 times greater than that of steel, and it's a lighter material. Something extremely interesting for the future, I would think. Okay, so this is the quick breeze through polymers, a good contrast to our discussion yesterday. I invite you to work your way through the worksheet and have a look at the world of polymer chemistry in a bit more detail. Thank you very much. Have a great night.